Hello, hello. Here I am, Retro Mark, with my now defunct U.S. Soccer Development Academy sweater. Crazy COVID's changed things around here. And my Starbucks recyclable cup that you can't get filled up at Starbucks, but you can make your own at home, so it's still usable. Today we'll finish up chapter 20 and we'll start chapter 20 acid derivatives, and then get on to chapter 21 amines. And happy late Mother's Day to all the moms out there. Hope you had a good day. And we got 2 weeks to go. Crazy. 2 weeks left. We'll have the final exam the final week, and we do have the nylon lab out there. So yep, I put the nylon synthesis online. Some of you have already done it, and I've gotten positive responses back. So it should be quick and easy, maybe an hour. It would only take you to go through the whole thing. And if you do it for me before Tuesday of this week, before tomorrow, I'll give you 2 points extra credit. So nice. Hopefully it's fun and easy for you, and get it done early, get it over with. And then exam 3 grading still in progress. I've been busy with the nylon synthesis, and the epic paper airplane retro has been dropped. The worldwide premiere happened Sunday night, Mother's Day 2020. Hope you guys enjoy it and share it with your friends and have fun with it. It's a fun one. Here's the link if you're at the outline that I post online. And keep turning in late reports, lab reports, and homework and corrections and stuff. And then I want to have the final exam on the same day, preferably the same time window next week. Let's see if we can get that done. So I'm going to send out an email to vote on a time. And so I was just throwing out a couple initially. I'll email out these, and you guys let me know. So I was thinking maybe the Thursday of next week. I know some of you have lab normally Monday, Wednesday, so let me know if you're like, oh, I don't want to do it Thursday. That's not my lab time. But it's kind of interesting, like the lab time thing. At first, I was trying to really keep with it, but then I have a lot of people who like requesting their exams on their lecture exams at different times because, well, then it was the lab exam. They had it at different times, but we'll figure it out. So I was thinking that Thursday would be good. Maybe start 9:30 to 4:30. I was thinking a 7-hour window. I'm not going to make it much longer than a normal exam. And then, or maybe 12 to 7, something like that. So email me if there's any special circumstances for you in that. Now for our VSOTW, pre-med student transferring to Sac State, oldest of 4 boys in his family, likes to play and watch sports, can't wait to get back to normal, but it has freed up more time for OChem study. Works at McCooney's and Dutch Brothers. Has learned to make great sushi. Fluent in Arabic. Lived in Saudi Arabia for his first 18 years. Can recite lines from the TV series The Office. And our VSOTW of the week. That doesn't make sense. That's like ATM machine. Our VSOTW is Amade. Let's give a warm Sierra College welcome to Amade. Okay, we're back at chapter 20. We're on outcome 6 now. This is the lithium hydride reduction of esters. So let's draw up an ester and see what happens when we add lithium aluminum hydride. Ether. Same conditions as we do with aldehydes and ketones. And what happens with this is you get 2 alcohols. You know what? I'm going to change this up, make it more obvious what's going on. I'll put like terbutyl there. And we're going to get an alcohol there. Plus an alcohol here. So you can see if I number this side, 1, 2, 3, I've got 1, 2, 3, 2 methyls off the 2. If I number the other side, 1, 2, 1, 2. So just completely reduces that guy. I'm going to do kind of a semi-partial mechanism, not a full mechanism. It's a long mechanism, and it's similar to the other ones you've seen. So I think if I show most of it, you'll get the idea. I won't ask you to show me any more of the mechanism than I show you. All right, so what happens is initially the aluminum hydride, which is very nucleophilic and basic, and not happy with that negative charge, it adds to the carbonyl because it's such a strong nucleophile, weak electrophile. I don't want a negative charge, adds in. You get your tetrahedral intermediate, and now aluminum should be happy, no longer a negative charge. But nope, it's not happy. I don't want a negative charge. I don't want, here it wasn't happy. I don't want a negative charge. And here it's not happy because I want an octet. So the oxygen does the classic Lewis base, Lewis acid, adds onto there, and we get the following. And now the aluminum, are you happy? You got an octet now? I don't want an octet. So you can, this step's a little bit crazy, but we're under very basic conditions. It can eliminate, it can drop the lone pair down and drop off what is a bad leaving group. But we're starting to see some bad leaving groups when we're under very basic conditions. And then the aluminum hydrides here. Oh, not hydride at that point. AlH3. And then we'll have this aluminum combined to that oxygen, the alkoxide, the ethoxide. Then you can see now you have an aldehyde. And we've seen aldehyde reductions with lithium aluminum hydride, so it's like we're already at the point where we have seen this step before. So aldehyde gets reduced down to the alcohol. And then after the acid workup, this gets protonated, that gets reduced and protonated. Oh, I lost the methyl, didn't I? I need you guys here to catch me sooner on those mistakes. So you can see multiple steps, but I hope you understand it. The key thing to notice here, this right here is the key step. And this is the same sort of step you saw with aldehydes and ketones and carboxylic acids. So this is the key step. We're going to now look at lithium aluminum hydride reduction of amides and see how it differs. So here we go. Let's make up an amide. Let's go make it a little bit interesting. Maybe put a ring on it. Okay. I'm cheating it a little bit. Not cheating, I'm just doing an easier one. If this nitrogen has, forget it. I won't cheat it, I'll put it on there. That has a hydrogen, the reaction is going to be a little bit different. Lithium aluminum hydride. We'll stop there. Okay, so if I do this reaction, what happens, it's interesting. Well, no, I'm going to go another step. Let's do sodium bicarbonate. What happens is instead of getting two different molecules, like you did with the ester, reduction, you got 2 alcohols. With this one, the product basically just looks like you erased the carbonyl. That carbonyl just got erased, huh? See how on this one, the carbonyl does go away, but we also break the bond between the carbonyl carbon and the oxygen. Here, the bond between the carbon and the nitrogen is not broken. So let's look at the mechanism, try to understand that. And I'm hoping you know why I added this as well, because under acidic conditions, this would be protonated. So this would deprotonate it at the end. Okay, let's look at I'm going to do like an abbreviated mechanism here as well, just the main parts here. So we have our aluminum hydride, which is a very strong base and a very strong nucleophile. But what's easier to do usually, be a nucleophile or be a base? Be a base if you're a very strong base. So instead of just attacking the carbonyl right away, it's going to deprotonate. The pKa of an amide is actually about 17. It's pretty acidic. It's like kind of like an enolate, you know, but it's the nitrogen version, so you can see why that would be a stronger acid than ketone or aldehyde. And you should also see that you make hydrogen gas, you got to be careful, that might explode on you. And you can see that this has resonance, that's why that pKa is 17. Okay, and if I don't have a hydrogen here, if I started off with just 2 methyls like I was initially going to do, you don't have to do this deprotonation step first. Okay, and then once this happens, you have the nitrogen can bond up with the aluminum. Yeah. Because that aluminum, is it happy without the negative charge? Nope, it's not happy because it has no octet. All right, now the aluminum needs to lose a hydride. It could, let's see, can it attack that one? 1, 2, 3, 4-membered ring? Might be tight. I think it's going to reduce something else. So let's say we have, I'll just make it a generic carbonyl here. So this could be one of these or something along another intermediate along the way. So it can add to that. Okay, now this guy can now be added to by another aluminum hydride of some sort. So it could be, another aluminum hydride, AlH4. It could be one of these or something along that line. So let's just make up a generic one, AlR3-. And that will add, and then we're going to see where the mechanism gets different than the ester. Well, it's already a bit different, but let's go to the next board. I'm going to keep up my key step there. And what I'm going to be explaining, I'll give you a little heads up while I'm erasing. So, what's more electron donating, an oxygen or a nitrogen? So remember, the oxygen's more electronegative, nitrogen's less electronegative. Who sounds like they'd be more of a donor? The nitrogen. We talked about that with amines, saying that they had a lot of resonance into the carbonyl that restricted rotation. And they were the weaker electrophiles because of all that donation. I'm missing a carbon, huh? There we go. Okay, so now at this point, in the other mechanism, this combined with aluminum, it can come back and forth. You can draw that if you like. But remember how before, well, actually, yeah, I'm going to do that. Sorry about that. Let's go AlR3. Let's bind that up right away. Okay. So now at this point, who's going to push off who? Do you think the oxygen's going to push off the nitrogen? Like the oxygen pushed off the oxygen, the ethoxy part? Is that going to push off the nitrogen? Or is the nitrogen going to push off the oxygen? So who's got the stronger push? Who's more electron donating? The nitrogen. So the nitrogen's going to push off. I don't really like that. Darn it. These mechanisms are just long. I try to shorten them up for you, but that's okay. Let's make this a so an H on there, an R and an R, R2H here. Sorry about that. We need to get rid of the minus on the aluminum. I don't want to have aluminum minus, oxygen minus right next to each other. So imagine this guy reducing. I'm going to go this way with it. Well, some kind of carbonyl. All right, so we get the hydride lost. And now we're into this situation where who's got the stronger push? The nitrogen or the oxygen? The nitrogen has the stronger push. So, you can draw it this way, if you'd like. You can see, no, let me draw it this way. The nitrogen pushing off the oxygen to give you this guy. And this is the key step for the amide reduction. The nitrogen is pushing off instead of See how this oxygen with the aluminum is the leaving group? But on the ester, that oxygen with the aluminum is not the leaving group. This is the leaving group. So we're comparing the ethoxy to the nitrogen. Ethoxy leaves, nitrogen stays. And for this reason, then you can see how another aluminum hydride source can come along. And reduce this once more and leave the nitrogen still intact on the molecule, not cleaving the bond between it. I'm going to get that. And then when you do, so you, before I say that, you can see how I gained 2 hydrogens here. The first one was early on. Boom, I got my first hydrogen on there. Now at this point I got my second hydrogen there. And then when you add the acid workup, you get to a point where you have the ammonium, because in an acidic solution, it'll be protonated. And you can add step C, which is the sodium bicarbonate, baking soda, which we've used to deprotonate a lot of these things, right? And then the carbonic acid breaks apart into CO2. And you get your bubbles. Okay, so let's do a couple quick overall reactions. Make sure you got the idea here. I drew up a couple nice examples for you. You should pause the video, try to fill them out. This one I separated the 3 steps of it because I want you to show the intermediate here and then the final product there. So go ahead, pause, try it out, and then come back. All right, welcome back. So this one's a cyclic ether. I mean, not ether, ester. So let's do it. It's going to give you the same sort of thing. It's going to completely reduce that. I'm going to expect an alcohol here and an alcohol there. So, and I better number these carbons, make sure I'm keeping track of them. So I got 1, 2, 3, 4. 1, 2, 3, 4. Yep, those are all my carbons I should have. And I just need another alcohol off of carbon 4, and that's it. The mechanism, remember, think of it as a hydride adds, you get the tetrahedral intermediate, and then that eventually the O- can kick off this bad leaving group, but under these very basic conditions. I kind of fumbled through the mechanism earlier, so, and these mechanisms are tough because I think there's just there's so many things that can happen at once. But I'll give you a clue. Know enough of the mechanisms so you can be good at the overall reactions, and probably won't get one of these mechanisms on the final, so just know enough to help you though, because it helps you learn it. So on this one, we get the hydride adding, get the O-, but now the O- and the nitrogen are competing as who's going to push who off. And it winds up the nitrogen is going to push off the oxygen. So I'm going to retain, I'm not going to break any nitrogen carbon bonds. And then under acidic conditions, this will be protonated, the amide. And maybe I'll number some carbons, make sure I got this right. 1, 2, 3, 4. That carbonyl just erased. It's gone, huh? And then when you add the sodium bicarb, just deprotonates it. There we go. The sodium bicarb makes CO2 and water to bubble away, right? 1, 2, 3, 4. So mechanistically, hydride adds. Hydride won't deprotonate this nitrogen, doesn't have a hydrogen. Adds O minus, binds with aluminum, comes off, and then eventually the nitrogen kicks that oxygen off. And then another hydride comes in. Okay. Next up in the outcomes was a reaction of a nitrile with an organometallic, but I'm gonna go ahead and skip that one and come back to it after. I think I should have nitrile reduction first because we were just doing reductions. So here we go, nitrile reduction. If we add to this nitrile lithium aluminum hydride, just like we did with the amides, a hydronium workup, an acidic workup, and then sodium bicarb at the end. What's going to happen is this reacts like what? Carbonyl, right? Reacts like carbonyl. It's going to get reduced all the way down to an amine. Let's make sure we're numbering the carbons and keeping track of everything. Looks good. And so I'll just go to the beginning of this mechanism too. It should make sense. We've been considering these like carbonyls for a while now. Okay, so we got the aluminum hydride. Is it happy with that negative charge? No, it's angry about the negative charge. I don't want a negative charge. So what does it do? It attacks the carbonyl-like nitrile. Adds on to there. So is the aluminum happy now? No more negative charge. Aluminum, isn't that nice? Nope. I want an octet. Nitrogen. Let's see that. So now, are you happy, aluminum? You got yourself a octet again. I don't want an octet. So it'll reduce another, maybe another nitrile. Anything that still can be reduced that runs into it. Okay, and now can you see how this guy is ready to add another hydride? It's like this was. I didn't want to add a hydride here because it seems to be too high energy to have an N minus directly attached to aluminum minus. So I have this give up a hydride first. So now that aluminum's not of negative, and now it's ready to add the second hydrogen. And then I'm thinking you can figure it out from there. It goes on to get, well, I gotta show that first. I should show that first. What am I doing? So now there's two hydrogens there. And then this can bond another aluminum. Eventually it gets acidic workup. It's going to be it'll be an ammonium, which you deprotonate to give you your. Let's try an overall. Let's try we'll try a synthesis of it, so we can make an amine. Let's go. Oh yeah, we can do. So I've got 1 carbon, 2 carbons, and I got 3 carbons there, huh? So you can see it's 3, 1, 2. Numbering's kind of weird the way I did it, but all right. So let's do this retro. Since you guys are the retro masters, I'm so excited about that retro paper airplane retro. That was Jeff's idea, by the way, the paper airplane. Good one, Jeff. Okay, so this can come from a nitrile we know now. And whenever you go to like triple bonded things, it's really easy to lose track of your carbons because you go from kinks to linear. So number those guys. And then this can come from SN2. Easy, right? So let's do the synthesis. Sodium cyanide, a great nucleophile, and maybe let's switch it up. Let's go acetone. Acetone is another polar but aprotic solvent, great for SN2. And then we'll treat this with the lithium aluminum hydride, acidic workup, and then finally quench the ammonium. We're learning how to make an amine in this chapter. In the next chapter, we'll learn other ways to make amines in the amine chapter. Now to finish off chapter 20, we have perhaps my favorite reaction in the chapter. Well, one of my favorites. I don't know, there's just certain ones you like more than others. I like these nitrile additions. So I'll show you what I mean. So if you have a nitrile, say this guy, if you treat it with an organometallic, say a grignard, I'm going to go THF this time, and then I do an acidic workup, and I follow it up with a sodium bicarb again. Oh, I'll put sodium carbonate for a second. Baking soda. So that guy actually adds into this and you get a ketone. So let's see what's going on here. Better number some carbons. Got 1, 2, 3. 1, 2, 3. And then over here for the Grignard, we got a 1, 2, 1, 2. It's an interesting reaction, huh? You're adding into the carbon, which is like a carbonyl, but normally when you add to a ketone or aldehyde, you wind up with an alcohol. You don't still retain a pi bond. So how are we going to figure this one out? Yep, mechanism, let's do it. So we have our nitrile, which is a weak electrophile, kind of like a carbonyl. Okay. And then our organolithium is a very strong nucleophile. So it's going to react right away. Going to add into the nitrile carbon. Get a new carbon-carbon bond. Get your magnesium and your bromide. I'm going to number this, make sure I did it right. So that's 1, 2 carbons for the Grignard. 1, 2 carbons, looking good. And then as far as the very basic Grignard part of the reaction, part A, it's done, that's all that happens. Another Grignard can't really add to this because if you added a second Grignard, it would make a double minus on the nitrogen. That's a bit much. And the nitrogen is not going to drop down and kick out an ethyl leaving group or an isopropyl leaving group, so it's got no leaving groups. So it's just done for this point of it. And then what happens is you add the hydronium and water, and of course it's going to protonate that. Walking it back. Okay, and then what is going to happen next? The solution is still acidic, so you probably already know what's going to happen, right? I need to get to the ketone. Are you already seeing it? Yeah, I'm just going to hydrate, and this is an amine, right? We're just hydrating the amine. So you had that on the last exam? I think I gave you an amine hydration, but it's similar. I'll do it real quick for you. So we already know this stuff. You're going to protonate that to make it a stronger electrophile. Now, water is a weak nucleophile, but strong enough to react with that strong electrophile. At this point, the water is the better leaving group, but we need it to stay. And there's a lot of water around, so. Trying to rush, and I didn't change up my colors on my curved arrows, which I really like. Let's get back to that. Okay. There we go. Now my oxygen's not as good of a leaving group. I forgot a carbon, didn't I? There we go. Okay, and I want to make the nitrogen a good leaving group, so let's do it. And what are we set up for now? Push-pull elimination, right? The oxygen oxygen lone pair pushes down, the nitrogen pulls towards its positive charge, and we're just about done. And the amine now can deprotonate that guy, or water, doesn't matter. So yeah, nitriles, when they're added to by an organometallic, this could be a lithium as well. They result in a ketone because after the first addition, it's done. And then when you add the acid and water, it's an old reaction we've already learned. We're going to finish off chapter 20 with a nice retro. If you want, start working on the retro. If you get stuck, pause, come back. So go ahead. All right, welcome back. So here we go. Oh, before I start though, let me look at this guy. I've got the 3-carbon unit here, and a 2-carbon unit here with the amide, and then I've got just a 1-carbon there with the cyanide. So let's try to figure out where those would come from. So the 3-carbon unit, I think it's got to be, this has got to be 3-carbon. And it looks like it's added at the middle, so that's like a Markovnikov type of opening there. And then another 3-carbon, I'm going to say 1, 2, 3 here as well. And that's going to be opening anti-Markovnikov off of 1. And then I'm seeing those 2 there on this side. That looks like those 2 from the amide. And finally the cyanide carbon, I think that's right there. Because that cyanide could be made into a carbonyl. Could be made into a ketone now, we know. Okay, so let's try the retro. Or actually, you should try the retro if you haven't already. Once you're stuck, come back. Here we go. All right, so the first thing I'm noticing is this guy is an imine. And I remember imines come from ketones or aldehydes and primary amines or ammonia. So this came from the ketone. And the primary amine. Yeah, I better number across here. I better count across. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, looks good. And now this primary amine can come from the amide we were given. Remember, we can do lithium aluminum hydride reduction, and it just erases that carbonyl. So there we go. And then the ketone, how do we get that? Yeah, I see it. I can go from either side. I think it's better to go from this side. Yeah, I think I didn't actually write the problem up that way, but I like this. I'm going to disconnect here. I can disconnect either side on this. You should practice that. Let's say I'll use a lithium in this case. And then my cyanide. I think I added an extra carbon. I'm going to leave it the way it is. I think it's wrong right now, but I'm going to number it, and I want to point it out to you guys like I did before. It's really important when you go from kinked to linear that you number your carbons. So let's label this like A, B, C, D. A, B, C, D. Oh, actually I did it right. I'm good. All right, so continuing on, this of course comes from the bromide, which we know how to get from the alkene, Markovnikov. And this can come from the sodium cyanide and the bromide primary, which can come from the alkene as well, but anti-Markovnikov. And we're good. Let's do the synthesis. I'll start off with my alkene. I'll make the lithium first. Why not? So in this case, I'll just add HBr to do the Markovnikov bromination. Put the bromine in the middle. Remember, you just think of that in terms of the curved air mechanism. Strong acid, what does it want to do? Protonate. Hinge on the end, open up to make the secondary carbocation and the bromide. The bromide adds there. You got it? And then we add the lithium. And we can pause there. Okay, and now we can also treat this alkene with HBr and some hydrogen peroxide. What happens there, remember, is the hydrogen peroxide breaks apart into radicals. The radicals could take off a hydrogen atom, making a bromine radical. Then when the bromine radical adds to the 1 position, it makes a secondary radical. And that's like the secondary carbocation from above. And this all results in anti-Markovnikov. And then we add the sodium cyanide and DMSO again, SN2. Let me make sure I did this right. 1, 2, 3, 1, 2, 3, looking good. And now I'll add my lithium. Okay. Let me make sure I'm doing this right. 1, 2, 3. 1, 2, 3. Yeah, it's looking good. Oh, I still haven't made my amine. Yeah, gotta make my amine. So I have the 2-carbon amide. If I treat that first with lithium aluminum hydride, then acidic workup, that will actually make the amine, but it'll be protonated. So I'll end up just deprotonating it, quenching it with sodium bicarbonate. And that gets me my primary amine. And I know primary amines and ketones will make imines. I'll put pause here. So yep, I add my ketone from above. Tossic acid. Remove water. Target molecules. Yeah, and then the diastereomers, E and Z. Whew, we did it. Chapter 20 is down. Let's go into our mechanism database. Let's see what we got in here. So if we scroll down to chapter 20, there's some good stuff in here for you if you want to check it out and practice. So you'll see Chapter 20, we have nitrile reduction and organometallic addition to a nitrile. The mechanisms. Let's look at these guys real quick so you can see. Got the overall reaction. Got the hydride adding, N minus, binds up, loses the minus, and now it's ready to be added to again, bind up, and then eventually it gets protonated. All the way down to this. Ammonium, and then the bicarbonate. And then here's one possible mechanism for the CO2 formation. It's got to be quick like that, right? Because you see those bubbles right away. And then we also have the Organometallic addition. So you got the overall reaction. We're adding an ethyl lithium. So you can see the addition. N minus, you get protonated. Now it's just about getting that nitrogen off. Weak electrophile, strong electrophile, weak nucleophile. Bad leaving group, 2 bad leaving groups, now 1 good leaving group. Push, pull, deprotonate. Bam. Chapter 21. Chapter 21 is amines. We've done a lot of amine stuff already, but we're going to do even more. So when you name amines according to the IUPAC rules, you just take the E part of the alkane name and replace it with amine. So I don't know why I gave the exception first. This is kind of a tricky one too. Before I look at these ones, let's do some easier ones. Let's draw them out on Marvin's sketch. Let's see what we get out of this. We'll go 5 carbons. Add an amine at the end. I like my lone pairs, so I'm going to go View, Advanced, Lone Pairs. There we go. Now let's get the name of this guy. Yep, that's one way to name it. I like to name it the way I was taught, the old-fashioned way. I put the 1 out front. But see, this is a 1, 2, 3, 4 carbon chain, so that's butane. So instead of writing butane, I just erase the E and add amine. So I would name this 1-butanamine, but they name it butane-1-amine. It's okay. Either answer is fine by me. Okay, let's make it a little more interesting. Let's add maybe a methyl here. There we go. Now how should we name it? Should we number 1, 2, 3, 4, 5, or should we name number 1, 2, 3, 4? Yeah, the 1, 2, 3, 4, 5. It's going to be a pentylamine, right? And is this R or S? Let's see. Nitrogen's highest priority, second highest, third. The H is back, easy. This is an S, 2S. Huh? Let's see what the name comes out as. Yep, that's how I would, almost the way I would name it. I'd name it as 2S 2 pentane, but then after my E pentane, I'm going to erase the E and write amine. There you go. They're just putting the 2 in another spot. Okay, now back to these original chapter outcome examples. So this first one, it's got an amine and an alcohol. And if you remember from the previous chapters, alcohols are considered higher priority than amines, just set by the old chemists bickering at each other at IUPAC, and they've come up with these rules. Alcohols, higher priority than amines. So we name this as an alcohol, not as an amine, so the proper name is numbering from the alcohol 1, 2, 3, 3 amino, 1 propanol. It wouldn't be correct to name it as an N-methyl group, 1 propanamine. Wait, no, I'm sorry, I was mixing things up. This isn't an alcohol as well. This is actually, I'm showing you, when you have a group on the nitrogen, you don't say this methyl's on like nitrogen number 1. You just say N-methyl. And then the N-methyl group is on carbon 1, 2, 3, like that. All right, remember spectroscopy of amines. A lot of this you already know. It's interesting how the primary amines could have 2 signals around 3300, whereas the secondary amine only has 1, and the tertiary has none. And let's check it out. Let's see if we can find some in SDBS. I just agree again for the 1000th time. Let's do a formula search. Let's go C4H. So if I went 9, 10, if I went 10, that would be C4H10 would be Doubling the 4, 8, plus 2 more is 10. That would be a fully saturated carbon. But if I add on a nitrogen, I have to add on another hydrogen. Remember the rules of degrees of unsaturation, the nitrogens subtract the hydrogen, so you need to add one. So let's check it out. Let's see. We have the diethylamine. Let's look at the diethylamine. So the diethylamine is actually, it only has one hydrogen off of the nitrogen. So look at that, a single peak there. And then the ethyl's sp3 carbon hydrogen is a little less than 3,000. Let's look at this carbon tetrachloride here. Usually the carbon tetrachloride for alcohols, it makes the peak stronger. I don't know what's going on with that one, but I like liquid film most. That's like the main one. Okay, let's move back to our results. Sec-butylamine, let's look at that one. Yep, so this amine is a NH2, so there's 2 hydrogens off the nitrogen, so it has 2 peaks around here. Isn't that nice? If you have 1 hydrogen, you have 1 peak. If you have 2 hydrogens, you have 2 peaks. Let's see what happens when you have 3 hydrogens. N-dimethyl. There we go. So this nitrogen has a lone pair, but no hydrogens directly attached, so no signal around 3300. Pretty nice, right? And then the other thing we want to look at, review, is yeah, this peak thing only applies when the alkane, when they're true amines attached to an sp3 carbon. Not when they're attached to a benzene ring. When they're attached to a benzene ring, an NH2, for example, on a benzene ring, if this was a phenyl ring, it winds up having 3 peaks. It's got an extra one due to resonance, I think, into the ring. All right, remember, when you have an odd number of nitrogens in your molecule, you have an odd mass spectrum molecular ion. There it is, 73, odd number, right? That's odd. This one's interesting. Yeah, so we got 70, 71, 72, 73. And then what do we have here at 74? Isotope peak, maybe 1 carbon 13 in the molecule. Okay, and then in the hydrogen NMR, it's very similar to alcohols. The nitrogen hydrogens can be washed away with D2O, and they show up in the same region. Let's look. Oops. Let me start some music. Oh, of course I picked the tertiary amine, so you don't expect any. Yeah, what was I doing? Return the results. All right, here we go. Let's look at that proton NMR. It looks like they're saying A, the nitrogen shows up here. Oh, it's actually, oh no, these two. That's C, sorry. A is this carbon hydrogen. So C is supposed to be around 1.25. So it's in a mix in here. So the hydrogens of an amine can show up from like an alcohol, 0.5 to 5 generally in that region. Let's look at the carbon NMR. Where do the carbons show up that are attached to this nitrogen? If they're like alcohols, they show up about 55, 60. And what do you know? Number 1 is at 48. There it is. Number 1 is at 48. Yeah, 48 right there. I'm sorry. Yeah, that's 48. That's 50. 48 parts per million, like an alcohol. Let's look at a couple more. Isobutylamine. Oh, I don't have the proton, but I got the carbon. So this carbon right here should be about 50-ish. There it is, 50. Right on the dot. Okay, so back to our outcomes. We got the NMR, and then this one is kind of scaring me. Well, not really, this one's not. You remember the pKa of these. They're very weak acids. Their pKa's are 35 for an amine. But when you protonate the amine and becomes an ammonium, now its pK is around 10. Now this is the one that's been getting me. We seem to be not doing well with our extraction diagrams, like especially on the aldehyde enigma lab. Let's look back at that really quick. So if you go into handouts, lab stuff, we got our monster extraction diagram. I'm just going to click download so I can animate through that. You guys are very good at this. Well, you should be, but it seems like you've forgotten when you did the aldehyde enigma, this reaction right here. If you have a carboxylic acid and it's in a basic solution, it will be deprotonated. It's very product favored. And when it's deprotonated, it's more water soluble, right? And you can reprotonate it if it's under acidic conditions. It gets reprotonated. Amines, though, they get protonated and more water soluble in acid, and they become less water. The ammonium becomes less water soluble when it becomes deprotonated in base. So you have your acid when it's neutral. It's not so water soluble. It's more organic soluble. When it's a carboxylate with charge, water soluble. Amines, opposite. Under acidic conditions are soluble, basic conditions are not. So if we're going to do our extreme extraction diagram again, I'm going to start clicking through this super fast. You guys should do this on your own. Practice it. Actually, I'm bored. I'll let you guys do it. So go to, I'm tired. Go to handouts. Lab stuff at the bottom. Monster extraction diagram. Let's see, where were we at? All right, next we're going to learn how to do amine synthesis. We've already done some. We're going to learn a few more.